Hey there guys, welcome to Unit 5 Notes D. The last notes that we're going to go over in Unit 5 are about molecular and empirical formulas. So what in the world could an empirical or molecular formula be? We've heard of formulas before, we've even practiced writing them. But what's the difference between an empirical formula and a molecular formula? Well, let's look at some examples. Can you see any patterns in these groupings? On this side I have a group of molecular formulas. On the other side, I have a group of empirical formulas. So what's the relationship between C6H12O6 and CH2O? It's the same relationship between N2O2 and NO, or C2H8 and CH4. So what is this pattern? Well, basically, an empirical formula is the reduced version of a molecular formula. A molecular formula, on the other hand, is the true formula. So actually, these molecules over here do exist on their own as well, so they could also be considered molecular formulas, but it doesn't work the other way around. In order to be considered an empirical formula, it has to be in the reduced version. So let's get some definitions down, starting with the empirical formula. So this is our reduced ratio. So not necessarily the true compound, although simplified ratios do exist in real life. If I say it's the empirical formula, it wouldn't be a good idea to assume that it's the true formula. So you can take a molecular formula and reduce it down, kind of like reducing to the lowest terms in fractions, and then that's going to give you the empirical formula. The way that we're actually going to use this today is actually to go from empirical formula up to the molecular formula by figuring out what the multiplier is. So it's this connection between empirical and molecular that really matters. So the molecular formula is the actual formula. It's really what exists. So the molecule with the correct number, not just the ratio, but the correct number of atoms would be our molecular formula. All right, so let's see first how we're going to come up with an empirical formula by looking at our first problem. First off, it tells me this compound is made of copper and oxygen. So our goal in coming up with an empirical formula is to determine the subscripts. How much copper compared to how much oxygen? What's the ratio there? So what it gives me is the number of grams of each. Now, can you compare the grams of one substance to the grams of another substance? Absolutely not. What's the one unit that you can use to compare two different substances? Well, it has to be in moles. So the first thing we have to do is convert gram to moles. If you haven't noticed by now, in this unit, if you're not sure what to do, convert to moles. That's often the first step. So let's start here with the copper, 2.199 grams. I'm gonna put that over 1. And then whatever I have on the top goes on the bottom. So the gram will go on the bottom, and on top we will put the number of moles. So the conversion factor for mole to gram is always 1 mole, and then we'll need the molar mass to put here on the bottom. So off our periodic table, for copper, that is 63.55. So that's going to allow us to calculate the number of moles for copper. Now I want to do the same thing for oxygen. The mass of oxygen I'm starting with is 0.277 grams. So I'll put that over 1. And then basically the same conversion factor, but this time I'm going to use the molar mass of oxygen. So a gram to the bottom, converting to moles, it is always 1 mole, and then we'll plug in the molar mass of oxygen, which is 16 even. So now we need to do a little calculating. The given grams divided by the molar mass should get me the number of moles of each. The idea here is to take our given grams, divide by the molar mass in order to get into the moles. So for copper, you should get 0.3460 moles, and then for oxygen, 0.0173 moles. Now that I have the number of moles, it's time for our next step. How do you compare two numbers? Well, we're going to make a ratio. So when we make this ratio, you always divide by the smallest. So what's smallest out of these two numbers? The 0.03 or the 0.01? It's the 0.01. So I'm going to take a number and divide it by itself. which is always going to give you 1. So that's normal in empirical formula. The smallest number of moles will end up with a 1-to-1 ratio, right? And then when I divide up here, I'm going to get a different number. So what is the 0.03460 divided by the 0.0173 from here? So once we set that up to divide by the lowest number of moles, you're going to get it 2 coppers and 1 oxygen. So what does that really mean if I have 2 coppers and 1 oxygen? Remember, we were trying to find our subscripts. So how could I indicate that I have 2 coppers? With a subscript. And how could I indicate that I have 1 oxygen? With a subscript. And you know, we don't usually write the 1. So we would just write that as C2O for our final empirical formula. We don't have enough information given in this example to take it all the way to the molecular formula. It's just how to get the empirical formula. So let's look at another problem. Notice it gives us a lot more information here. Let's go through and kind of highlight what we're given. We have a percentage of carbon, percentage of oxygen, and a percentage of hydrogen. The only other number in this word problem is 62 grams per mole. Keep in mind what grams per mole usually measures, or molar mass. We're going to need the molar mass to go from empirical to molecular formula. But first, we have to figure out how to use this first sentence to get an empirical formula. The catch here is they gave us percentages. So how are we supposed to figure out how many grams from a given percentage? Well, if we knew the total amount of grams, I could find the percent of that number. But they didn't give us a total amount of grams. Instead, they just gave us the percentages, right? So we need to figure out a total amount to use. And it really doesn't matter what the total amount is. You could pick any number. What is the easiest number to find a percentage of? 100. So if we just assumed there's 100 grams, then we could find the percentage of 100 grams, which is going to be a very simple calculation, right? Basically, it would be 38.7 grams, 51.6 grams, and 9.7 grams. So because it doesn't matter what you're finding the percentage of, basically that means the shortcut here, just bottom line, just use the percentages as grams for your starting point. But then what's the next thing we're going to have to do? Think back to the last question. We can't compare gram to gram. You have to compare mole to mole. So first thing we'll have to do after we get these into grams is convert to moles. Then we'll be able to compare the moles and start doing what we did last time. All right, so let's start with our carbon. So we said carbon has 38.7% of 100 grams would just be 38.7 grams. So I'll put that over 1. And then just like we did before, since we're given grams, grams will go on the bottom and we'll put moles on top. It's always 1 mole. And since this is carbon, I'll use the molar mass of 12.01. If I do this for oxygen, I'm going to start with the 51.6 grams, put that over 1. Again, given grams, so grams goes on the bottom, mole on top. Always 1 mole. The molar that mass this time for oxygen, 16. And then the last but not least, we have our hydrogen. So the hydrogen was 9.7% of 100, or 9.7 grams. All right, and so since I'm given grams, that goes on the bottom, and we convert to moles. Still 1 mole, but this time the molar mass for hydrogen, 1.01. So if I do this division, essentially what we're doing here is dividing by the molar mass. That's going to convert grams to moles. We're going to be able to get our 3 different moles. So now we've got to think, if I've got moles of each one, how am I going to compare them? Remember, comparison means a ratio. So what am I going to divide by? Always the smallest. So the smallest moles out of these 3 would be the first one, the 3.22. So I'm going to divide by 3.22. All right, and something divided by itself is, of course, 1. This is pretty much 1, right? Close enough. And then just look here at the beginning, 9 divided by 3, 6 divided by 2. This is pretty much 3. And you can pop that in the calculator and see we're very close to 3. So we have a 1 to 1 to 3 ratio. What do we do with those final ratio numbers? Because they tell me I need 1 carbon, 1 oxygen, and 1 hydrogen. So how do I represent the number of atoms in a compound? I'm going to put them in as the subscripts. So here's my division, divide by the smallest. And then I'm going to put them in as the subscripts, CH3O. If you're wondering how we order these elements, remember carbon usually goes first, unless it's an acid, and then you're going to put them in order of increasing electronegativity. So that's how come oxygen ends up at the end there. So we've got CH3O. Now, we still haven't used this molar mass. We got our empirical formula, but now I have to convert to the molecular formula, and the molar mass is the key. If I found the molar mass of my base format, my empirical formula, I can then compare that to the molar mass that we're supposed to have. So let's go ahead and calculate this. What is the molar mass of CH3O? 12, 1.01, and 16, or 12.01, 1.01 3 times, and 16. What do we get for the empirical formula's molar mass? So if we add that all up, we should get a molar mass of about 32, 31.04. So is this empirical formula with the molar mass of 31 the same as 62? No, these things don't match. If they did match, then your empirical formula is the molecule also. But they don't match. As a matter of fact, it seems that the molar mass of the real molecule is pretty much twice the molar mass of the base unit. So if I have twice the molar mass, I must have twice as many atoms. So that's actually called the multiplying factor, being able to basically divide the given molar mass by the simplified or empirical molar mass. So if you do your molecular divided by your empirical, you get what to multiply the empirical by to get to the molecular. So if we take the subscripts that we were given in the empirical and we multiply those by 2, our multiplying factor, we will get the molecular formula of C2H6O2. Because the molar mass was twice as big, the molecule must have twice as many atoms. So that's how we get our empirical formula to turn into the molecular formula. Pretty nifty trick. The molecular formula is what really exists, but you have to start with the empirical formula to get the ratio and then compare the molar masses. All right, one last hiccup that might come up here. What if the mole ratios don't come out even? Before, when we were dividing by the smallest moles, we were very, very close to whole numbers. But what if we're not so close? What should we do then? Well, let's look at one last example where this is going to happen. Here I'm given the grams of aluminum and the grams of oxygen. So that tells me that I'm looking for aluminum subscript and oxygen subscript. But I need to be able to compare the amounts given. Can we compare gram to gram? Of course, the answer is still no. So what do we need to convert it to? Gram to mole. So I'm going to start with my aluminum, and I'm going to have 2.42 grams over 1. And then just like we did before, I'm going to put the gram on the bottom and mole on top. Always 1 mole, and we want to put here with gram, always the molar mass. So for aluminum, let me look that up real quick. We got 26.98. All right, now let's do that for oxygen. For oxygen, we're starting with 2.15 grams. We'll put that over 1. And then again, gram to the bottom and mole on top. Always 1 mole. And then the molar mass for oxygen now is 16 even. So if I take the given grams and divide it by the molar mass, that's going to get me the moles of each atom. Then I can compare them. So let's see what we get for that. For aluminum, it's 0.0897 moles, And for oxygen, it's 0.134 moles. So which is smaller? Now we want to divide by the smallest. 0.0897 or 0.134? 0.08 would be smaller. So I'm going to divide by the smallest. So the one that's divided by itself ends up being 1. And when I divide this, what do you get now? Go ahead and do this one in the calculator because I want to know exactly what it is before we start thinking about rounding. We get 1.495. So basically the ratio of aluminum would be 1 aluminum to like 1.5 oxygens. Have you ever seen a subscript with a decimal place? No, doesn't happen. So how could I get this ratio to be represented as whole numbers? Well, should I round the 1 all the way down to 1? Like, is this a 1-to-1 ratio? That's not quite right. Should I round it up to 2? Is this a 1-to-2 ratio? Still not quite right. So how could I represent the 1 to 1.5 ratio as whole numbers? We can just double it. We can get 2 aluminums to be equal to 3 oxygen. And that is the exact same ratio as 1 to 1.5, but as whole numbers, which is exactly what we're going for here. So if the mole ratio comes out to a number that's closer to the middle, you multiply by 2. If it comes out to like 1.3, you got a third, multiply by 3. You have to multiply by a number to get the whole numbers. If it's like within a 0.1, or here it is, within 0.1, like if you get 1.9, you could round that up to 2. Or if you get 1.03, we can round that down to 1. So a little rounding is okay. But if it's too far, you've got to find another multiplier, a multiplier to get those up to whole numbers and preserve that ratio. So our final answer is Al2O3. Another trick you can use to kind of check yourself, if you know the ionic charges, like Al is +3 and oxygen is -2, remember you have the crisscross. Al2O3. Same thing we got, that's supposed to be an arrow. Same thing we got through our mole conversions. Alrighty, so that's gonna wrap up our molecular empirical formulas, and with that, all the notes from Unit 5. So the next notes that you'll be looking for are actually for Unit 6, where we're gonna start looking at chemical reactions. I'll see you there.